Everyone, this is my lab report for Physics 2011, Lab 1 Constant Velocity. My name is Manav Mihir Patel. Okay, so first we'll start with the purpose of this lab, which is to observe the motion of an object, which in this case is a water bottle moving with constant velocity, using a software program called Tracker. And then we'll compare this observed position to the computational model predicted position. Alright, the principles that here are the physics principles that we are going to use throughout the lab. First is Newton's first law, which says that an object will remain at rest or continue to move at a constant velocity unless acted upon by an external force. The next is Newton's second law, which states that the net force acting on an object, F net, is equal to the mass of the object divided by its acceleration. Here's the formula for it. This law implies that an object's acceleration is directly proportional to the net force acting on it and inversely proportional to its mass. If an object is moving at a constant velocity, then there is no acceleration and therefore no net force acting on the object. Results. Here's a brief preview of the results that are going to be proved in the lab. The computational model's position time graph was more linear than the observed one, and the observed one's position was traveled more than the computational model's position. Assumptions that we're going to take throughout the lab. The friction and air resistance are assumed to be zero or negligible. The net force is assumed to be zero because the object is at constant velocity. So here's what's going to happen in the lab. A water bottle was rolled on the floor at a constant velocity, and it was recorded and analyzed using Tracker. The focus of the analysis is the water bottle itself, which is considered the system in this experiment. The surroundings include everything that affects the water bottle, such as the floor, air, and any applied forces. The forces acting on the bottles include applied force, the initial force used to set the bottle in motion; gravity, the downward force due to the Earth's gravity; and friction, the opposing force that includes rolling friction and air resistance. CloseScript was also used to create a computational model for this. These are the equations that we are going to use in the lab. The first is velocity update formula, which is the final velocity equals initial velocity plus net force over mass times delta t, which is change in time. The average velocity, which is final position minus initial position all divided by change in time. And the position update formula. Final position equals initial position plus average velocity times delta t. This is the video that was used of the water bottle rolling on the floor. Yeah, this is the observational model of the video, which was used during the Tracker. Here's the graph for it, and here's the data for it. So the average velocity for this was calculated using the average velocity formula that I showed earlier, which was final position minus initial position all divided by change in time, where the initial position was negative 0.0415, 0, 0. The initial time was 0 seconds, and the final position was negative 1.391 in the x direction, and the final time was 0.933 seconds. So the average velocity after calculating it was negative 1.446 meters per second. Here's the table that I used to calculate the average velocity. Here's the computation model's velocity versus time graph. and position versus time graph, and the data. This is the code that was used for it. So the initial position was negative 0.0415, which I got from the observational model before. The average velocity was negative 1.446, which I also got from the observational model. And time was 0.933 seconds. The mass was changed from 1 kilograms to 0.000283 kilograms in line 32. The initial position and velocity were also changed to negative 0.0415 in x direction and negative 1.446 in the x direction, respectively, on lines 36 and 37. The delta t was changed to 0.0667 to match with the observational model at line 41. At line 50, the time was changed from t is less than 0 to t less than 1 to match with the observational model time. At line 55, the fnet was changed to 0. And at line 59 and 61 demonstrate the velocity update formula and the position update formula, respectively. Here's the code for it. Alright, now let's compare both models. As you can see that the observational model has traveled further than the computational model. This is simply because the computational model assumes that the net force is 0, whereas the net force isn't 0 for the observational model because of other forces acting on the bottle like friction and air resistance, and because it traveled more in the observational model, the applied force was greater than the frictional force and air resistance combined, rather than being equal. This is the table for the observational model, and this is the table for the computational model. The errors that could have happened throughout the lab were human error, force acted on the bottle by friction and air resistance. It could also be that the manual tracking of the bottle's position in the tracker wasn't really precise. So what if the positive x direction and the negative x directions were swapped? The slope of the graph would be positive instead of negative, but everything else would basically remain unchanged, like the equations of the lab and the results of the lab. Now, what does it mean if the net force is not 0 in the experimental model? Now, this is because it accounts for factors like air resistance, friction, and the force applied to the bottle. This is the reason that both data weren't equivalent. Thank you for listening to me. I hope you have a great day.